artificial intelligence, and the healthcare use case opportunities are growing at warp speed for this type of technology. Pharma is quite eager to integrate new solutions to enrich the R&D processes and results. We kick off today with insights of how an out-of-the-box artificial intelligence solution is helping to solve some of pharma's greatest challenges. So joining us from Germany is Dr. Peter Neubeck, a trained doctor, MD, and an experienced life science venture capitalist turned entrepreneur. Let's welcome him to the stage. Thanks.
Good morning. Can everyone hear me? Sounds like it. Sorry you had to wait a little bit. We had some old world problems in terms of displays and resolutions and everything, because I actually want to give you also a little bit of a live demo, because I think one of the challenges for the customers of this type of new product that we're all talking about here, AI, big data analysis, mining, is that it's very difficult to grasp. I mean, everyone knows about the buzzwords, AI, big data, but what does that actually mean for the persons in their daily activities? You know, how do you actually translate these technologies, these very advanced technologies, into a product that is actually doing something for the persons who are actually working with whatever they do in their regular lives? And here we're talking about pharma, and with EXB, we have come up with a project and product, essentially, which, if you compare it to other solutions out there, which obviously have a lot more advertising power and manpower, if you think of IBM Watson, if you think about companies like Palantir, these are obviously behemoths of AI and data mining. And EXB is a 50-person company based in Munich and in Leipzig, which is trying to do a successful version of the David-Goliath game. And I think so far we're doing not too bad. I mean, EXB, if you were wondering, stands for external brain. And the reason for that is that the founder and the IT brain of this company, which is obviously not me, because I'm a stupid physician, but the founder, he's a guy who was one of the first computer linguistics students in Germany in the mid-90s, and he started out with a project comparable to what is Siri today, or any sort of speech recognition technology. And then he moved away from that and created something which, let's see if I can drive this. Anything is happening here. I'm trying to do the next one, but it's not giving me the next. Let's see if I press longer. Ah, there we go. Hopefully we're staying there now. Okay, so the first technology that EXB has actually developed and commercialized and successfully sold was next word prediction. I guess every one of you knows what that is. Some of you might like it, some of you might hate it. But essentially it is, you try to type a sentence with your cell phone, and you start with typing hello, and the machine is predicting the next word will be a name, or it could be you start out with good, and the machine is predicting the next word to be morning, appetite, evening. That is what next word prediction is, and our IT founder was one of the guys actually inventing this, and he sold this package to Nokia in 2010. This was commercialized in all of the operating systems at that time, running in over 100 million phones. So I think even though we are a small company, we're a company that is able actually to take a new technology, a new idea, a new paradigm to a product. And luckily enough, that exit also enabled the company to be financed quite nicely. So we don't have any VCs in our company, although that's my heritage, but this company actually is pretty much owned by the founders, which is quite comfortable. And we're now moving on to the next stage. I mean, and if you take this as a background, I mean, this company has been starting out with working on the small cell phone architecture. And think about sort of what we're trying to do here now. We're working with huge data masses, trying to analyze these data masses. And the company having already sort of the engineering and IT know-how of how to do that on a cell phone architecture, moving that now into a cloud is also of benefit, depending on what you want to do with that. But that's sort of as a background. Let's see if this goes quicker. There we go. So now we're talking about EXB Health. I'm mentioning that because, as you can imagine, and that's also one of the problems if you talk to any life science or healthcare customers. I mean, this technology that we're talking about here is obviously domain unspecific. Essentially it has nothing to do with health. Essentially we're talking about how to read texts or images or any kind of other data with human precision. That's how we define what we're doing. Cognitive computing is to sort of analyze data as a human with the precision of a human being. And obviously that can be all kinds of data. And EXB, as you can imagine, we're being from Munich, big automotive company, automotive city. We're also working in the automotive mobility space, as you can imagine. Another important aspect were, if you think about self-driving cars, if you think about the whole interconnectivity between your own cell phone data and the continuous data flow that a canvas system of a car is producing, makes obviously sense to apply this technology also in the mobility and car space. But we're talking about health here, which is also our main focus. So what is EXB exactly doing? I mean, I mentioned it already. I'm trying to phrase this again, and I'm always looking at this as the customer and also as the guinea pig, because when I met EXB, you know, again, coming from a full-blown pharma, biotech, medical background, having not really been exposed to any sort of high-tech IT company before, this was all very new to me. And again, I think it all starts out with framing actually, what are we trying to solve here? And every one of you guys knows, I mean, all the buzzwords regarding big data, sparse data, what do we do with data, how do we mine data? And I think this whole issue starts out with that knowledge explosion that we have often been facing. You know, I mean, when I went to medical school in the early 90s, you know, we were still working with books for the most time. I mean, this is all history by now. And if you think about sort of the sheer mass of articles popping up every day on PubMed, just trying to keep abreast with a small field in science is already almost not possible anymore. I mean, I did my thesis in coronary remodeling and cardiology. Even if I were doing just that, just staying abreast with that tiny sort of piece of data within that universe of healthcare data is already difficult. So the first question is, how do you get that data into sort of a mode where you can actually sort of work with it in an efficient way, and then how to mine that data? And for a company like EXB, this is obviously exactly the field that we're working in. So this knowledge explosion is an opportunity for a company that can, first of all, integrate data in a way that you can analyze it, that can analyze the data. So that's really what we're all about. To put into perspective what we're doing in terms of vision, you know, EXB is really, as I said, a machine that understands language, that understands texts, images. And if you think of how a pharma or a biotech is usually looking at data and different data sources, you know, there's usually two interesting silos that we also discuss with customers. I mean, one silo is the internal data. It's all the data that a big pharma or biotech is producing on an ongoing basis. And I'm just listing some of them here, and you all know this data. Maybe just to note, I mean, that type of data is also important. This is a combination, a mixture of structured and unstructured data. You all know that unstructured data is a different animal. In the end, the unstructured part is what we're really focusing on here. Structured data is something that can be analyzed by other technologies. But in the end, you want a machine that can do both, that can do unstructured and structured data, and it also can do different data modalities. If you think about this data, you know, this can come in various forms. This can be Excel lists, this can be PDFs, this can be PowerPoint presentations, this can be even emails. So whatever you have, the data comes in different forms and shapes. And first of all, you have to get it into the machine. And once you have it in the machine, you have to sort of analyze it in an efficient way. So the whole topic here is, first of all, what we want to do is we've built a machine that gives you the chance to import all kinds of data. It can be your internal or your external data. The package that we're selling right out of the box or off the shelf obviously comes with publicly available data. So think of PubMed, think of the 28 million abstracts that are freely available, think of the roughly 10-15% of free full text that is in PubMed. Think of databases like the US Patent Database, the EPO, the European Patent Database. Think of websites like clinicaltrials.gov. Think of the company websites. So everything that sort of is publicly crawlable in a sense is already something that you can use this machine right away with. What our customers, for the most part, also want, at least in a second step, is that they want to hook their internal data into the system, because obviously the power of this whole idea becomes very prominent once you start sort of combining the data sources. So you have your internal data that's been generated. Let's think about sort of discovery. So you have different candidate properties, you have different IP sources, whatever you have, and you want to combine and compare this data with all the data that's out there in the universe, and which is constantly changing. And again, the company, as it has both research and engineering capabilities, is certainly able to technically work with the customer of how to get this data into the machine. And as you can imagine, it was mentioned already before, if we're talking about sensitive pharma data, patient data, It's all a question of also how to keep that safe and secure. And our solution is also flexible enough to be used on-premise. I mean, it's a cloud-based version, it's a server-based version, but it can be also running. I mean, if we're talking to pharma, we usually talk about sort of on-premise solutions, which makes perfect sense because any pharma or any academic institution does not want to get any of that data out of their own hands, and we will make sure that that's not happening. So once we have that data in the machine, our main sort of thrusts, what we're working on is in pharma, it's all about sort of R&D process optimization in the end. I mean, can I get quicker through a sort of quick and dirty iterative way through data to get to the points where I'm trying to get? And I will talk about this a little bit more in a second. As you know, the R&D process is a very innovative process. It's a very sort of unstructured process, and it's always looking for the non-obvious. And I think this is sort of one theme that I want to also get to you, that this is an engine that will help you sort of grasp the non-obvious in data, because you're always looking for new things, and you usually don't even know what you're looking for. It sounds kind of strange, but that's usually how the research project works, and you have to sort of build a machine that can actually help you do that in an efficient way. But there is obviously lots of other applications beyond the sphere of biotech and pharma. And we're talking to all kinds of players within the healthcare continuum, be it payers, providers, clinics. So I'll tell you some more about that, but let's stick to pharma, health, and biotech before. I mean, I'm not sure how many of you are sort of biotech pharma people versus IT people, but I'll try to keep this short. I mean, the application in the R&D process is obvious. I mean, in the end, we're talking again about sort of lots of data in a very inefficient process. I mean, I've worked with Novartis, so I have big pharma experience. I've also founded and created small biotechs, which are very virtual. But in both cases, you know, you always have this problem that the process is a gamble. It's a casino, essentially, and pharma is recognizing that, obviously. I mean, it cannot go on like that. I mean, the margins have been good in the last 50 years, but the margins will get worse. For good reasons, sometimes, if you think about sort of drug pricing and other issues. So I think pharma has to sort of change and become more productive in terms of how they develop new drugs. You know, this funnel, the very famous funnel of sort of starting out with 10,000 molecules and ending up with one on the bedside is not going to be working in the future. It's just simply too expensive. So, and along that way, I mean, obviously there's lots of sort of data being produced all the time. And just imagine that you could compress and change the format of this funnel to something where you can already sort of eliminate more drugs in the beginning. You can shorten the time because you can make smarter go, no-go decisions along the way up to the discovery. And then by that, sort of increase the number of candidates which actually reach the clinic, and then really do very focused clinical trials that can help in the end, hopefully, to make this process just a little bit more efficacious. You know, we're not talking about that this solution will be changing everything. You will still use your pipette, you will still use animals, you know, rats and dogs and cats and baboons and whatever, and you will obviously have to test the drug in the patient. So we're not going 100% in silico, that would be stupid, I think, at least not for the next 50 to 100 years. But software will certainly play a bigger role. I think that's also an obvious thing. So we'll have to see how that turns out. But in the end, I think it gives you sort of a picture of why pharma is also interested in this. I mean, there is a strong pressure to become more productive. Just to get a little bit more concrete, what are we talking about here? And what is actually sort of what are the questions that people are asking us to sort of solve? And I don't want to go into too much detail here, but maybe if we just look at this table for a quick second here, the use cases are very concrete. And I think this is also a very important factor. I mean, I've been, I don't know who's from IBM, no offense, but you know, I've been to demonstrations from IBM, which are very, very nice, you know, fluffy slides, and you see a lot of great stuff, but then once it gets concrete, you're sort of at a loss. And I think that's not really working well with pharma. I mean, pharma is willing to spend money, serious money on software, but it needs to see a concrete application. And I'm just mentioning some of the things that we're doing with pharma. So use cases like drug repurposing, drug discovery, you know, and then even going one step further. You know, if you do something in drug discovery, you know, what are you actually trying to answer? I'm just giving you the first bullet here where I'm saying, which targets make sense for which indications? You know, sounds like a almost trivial question, but it isn't. You know, if you start out with a project and you're thinking about certain molecules and you're thinking, okay, which indications actually make best sense here? You know, it might not be the obvious indications. There might be others that you need to think of, and to actually sort of hone into this question and use sort of the sparse data that is around there, you have to have a machine that actually can go through data in a way that helps you answering this question a little bit more. It will never answer the question 100%, but it will give you a chance to sort of do this by yourself and also do it in a very efficient way. Because if you think about the conventional approach in the third column, you see, let's say, very mundane ways of doing this nowadays. And usually pharma is outsourcing this type of data to service companies who manually curate data and go through data. Because in the end, first of all, they don't have time themselves, and they can't really use, you can't do that by just using Google or using PubMed, because yes, you can search for certain key items, and there are some more advanced sort of PubMeds out there, which can give you some more sort of semantic search capabilities, but it always stops somewhere. And it needs to go one step further for pharma to be really relevant. And in the end, the system that we have built and that we have also built out of the box is a system which you can log on, and let's hope it's working, because I actually really want to show you some software. It comes already with a preset application that can give you sort of a right out of the box solution where you can start importing data, you can define what kind of data you want to look at, and then you can sort of go through that data asking some of these questions. You're asking, for example, relationships between gene and gene relation and gene products, relationships between diseases and certain targets. So very concrete questions that you or that pharma researchers usually have. You can take that obviously to other areas like competitive intelligence, to scientific activity. Imagine you could actually, before you go to a big conference, and I'm not talking about a conference like Bio, but I'm talking a medical conference like ASCO or AHA, and you want to sort of go systematically through the website and through all the abstracts and all the speakers and want to sort of understand before you go there what is really relevant. And this is very cumbersome to do nowadays because you have to do it manually and try to do it somehow, but it'll never work really well. But if you had a machine that can do that for you and really pick out the things that you're interested in. So all of these things are just very concrete, and I'm stressing that because you cannot sell this type of sort of application to pharma if you're not as concrete as possible. And again, we're talking about as our out-of-the-box solution, we're talking about a solution which is not that expensive. It's a simple license, and it's something that's where also the hurdle of pharma, so to just try it out, license it, and see what it does, is certainly something that they are much more sort of amenable to, rather than going to them like some of our big competitors are doing and telling them, look, we can build you anything, just give us 10 million up front and we'll start hacking away and building something for you. Maybe it's working, maybe it's not. Obviously, we can't do that. So we have to come with a concrete product. And I think that's also our claim to fame, because I mean, there is no one out there who has such a product. I mean, IBM is now coming up with a drug discovery tool, which I have seen myself, but which is certainly, in terms of what it actually offers, just a small start compared to where we are right now. If we go on, let's see if it's doing something. There we go. I'm not spending any time on this one, but you can imagine that there's also lots of applications in non-pharma, non-biotech, especially in the field of sort of disease management. So if you think about medtech diagnostics, the providers, the payers, because the questions are similar. You always try to sort of make sense of unstructured data. Think of how great would it be if I could actually analyze the doctor's letters, unstructured data, complex. It's not easy. You cannot mine, free-flowing text in a very smart way. But this is exactly the stuff that people want to do. They want to combine also different data modalities. So they want to look at, for example, think of Alzheimer's, for example. You have patients who get continuous examinations. They get also usually longitudinal imaging, CAT scans or MRIs, and you have obviously all the doctor's notes.
About how much?
Right now, there's no system out there in the world which can actually merge that data, which can look longitudinally across, looking at the CT scans, at the MRIs, comparing to the natural disease evolution, comparing it to whatever disease drug modification the patient was on, what kind of results that had. Think about sort of mashing the data together and coming up with new solutions. And as always, I mean, you're looking for either new diagnostic paradigms, new treatment paradigms.
My first thing is like when you have slides like that for like an audience like this, people just.
How do we do it? Again, I'm just a stupid physician, so I'm not talking any tech about here. But the only thing I want to say here is, I mean, we have a full tech stack, which means this company is really built from scratch in terms of having its own algorithms and using obviously also everything that's out there, which means there's obviously publicly available. deep learning algorithms, and we're also using them. We're combining them with our own IP. As much as IP is protectable, we're protecting things, other things are obviously secret. But it's the full stack that's able to do everything that you need to do with mining text efficiently and also doing images. And I think that's also another thing I want to stress. At least to our knowledge, there's not really, I mean, many people are claiming that, but we have actually a system in our workbench which can do text and images already in one solution. And I think in the end, if you think about sort of how you work as a physician, as a researcher, there's a lot of things where there's text and visual information, image information, which you would like to analyze at the same time. And we can do all that. So I think you see we have all that. As I mentioned before, we can hook onto the system any databases that are necessary. And we have obviously also tried to build a system which is sort of also from a user interface and user experience, a tool which comes across as intuitive as possible.
Exactly.
Trying to speed up a little bit. This one here is just showing you we have obviously done our homework in terms of comparing ourselves to the competitors as much as possible. So if you think about sort of text recognition performance, and I'm not going into details because there's no time, we have done that where it's possible, and in the space of natural language processing, you know, IBM autonomy and also HP autonomy and IBM. Are certainly gold standards, and you want to compare against them. And especially if you look at sort of more medical terms, I mean, broad terms like places, people, they might be doing okay. But once you get into medical stuff, I'm not talking only about recognizing diseases. I'm talking about recognizing properties of diseases, units, values. That's where these people have, at least they don't have anything right out of the bat. They can probably build that for you, but they probably will not have it right there.
Accessible and learn, exactly, they want to learn
the workbench itself looks like this. Again, I'm hoping that I can still show you that for a quick second, but I think you can already grasp here it's a system which is built in a modular, intuitive way where you first design or define what kind of data you want to work in. And as a second step, you say, okay, what am I actually going to do with this data? What kind of things am I looking at? For example, I'm looking for a set of 10,000, 100,000 abstracts from PubMed on a certain disease or a certain target. And I then want to sort of, within that data, want to do certain things. For example, want to look for compound properties. I want to look for gene-disease relationships. I want to look for gene-product relationships. And then you get an output, and you have a way also to share this with your colleagues. So if you have done an analysis like this, and the analysis time depends obviously on how much data you do. So I mean, if you do 1,000 abstracts or 1,000 publications, it's quick. I mean, the whole thing takes less than an hour. If you do this obviously with 10,000 or 100,000, it will take longer. Although the technology behind it is certainly completely scalable. It depends on how many nodes you have, on how many graphic cards. You can certainly scale this up much more. But again, that's also something we're doing with the customer depending on what he needs. I'll show you more once we go live. Just a quick grasp again on what we're doing. We're always looking at the non-obvious, as I mentioned already. So we're trying to answer questions where it's usually not even clear what the question should be in the end. And it's all about sort of finding new targets. And the way we're displaying that, there's different ways of visualizing that. There's knowledge graph, there's depictions like you see on the lower left-hand side. There can be also simple lists where you see frequencies. You know, I mean, one of the first use cases we had with one of the biotechs we're working with, they had a certain target, and they wanted to find out, okay, how has this target been associated with all kinds of diseases and indications in the PubMed space? And this sounds sort of trivial, but it's difficult to do. I mean, you can plug this into PubMed or Google and it will give you sort of a haystack of data. But if you want a frequency list and you're not interested in what's up there on the top, you know that this molecule is known to work in certain tumors, for example. But what you don't know is what is sort of on position 10,012, because that might be the thing you're looking for. So it's always sort of looking for the non-obvious in data. If we're looking at sort of specific text, here you have an example of how we sort of really look into diving deep into the text. So you see on the upper hand example a certain relation between a certain drug and its properties. In this case, it's a PI3 kinase inhibitor, Idealizib from Gilead. And what the machine has here done, I mean, this was an analysis that was looking at compound properties for PI3 kinase inhibitors. And for the example of Idealizib, it found, for example, that it is a potent and selective inhibitor of PI3 kinase. And you see very nicely also below in the text, so this is sort of in the source text, how the machine has actually read
like,
that text.
see,
I think this is a good point
myself
to make one more point here.
Do,
We're not built on, for the technical people here in the room, this is not simple co-occurrence.
if you want.
This is actually what
That's up
IBM
to
is
you.
mainly doing co-occurrence.
It's
if
up
they
to
do
you.
natural
It's
language
if you
processing.
want to
They're
do it,
looking
fine. If not, I can
is a
just, you know,
certain
it's gonna
word
be so we do this,
in the
blah, blah,
vicinity
blah,
of
blah,
another
blah,
word.
Keep talking. So,
That's
you know.
nice, but it's not good enough for Pharma.
Yeah.
Pharma wants relations. Pharma wants sort of a clear
Oh, you did?
relation
Awesome.
between
What
a certain
panel were you on?
gene and a gene product. It's not good enough that this gene is mentioned in the same paragraph as that gene product. There has to be a relation. The machine has to be trained to find relations, and that's what we have done. And I'll show you another example in the space of image recognition. I mean, again, we're doing the same for images. And I think one thing I didn't mention yet is that the machine is very easily trainable by yourself. I mean, we're not definitely expecting our customers to do that, but if people feel like they want to train the machine on their own concepts, they can certainly do so. For the most part, we're doing it for them, and we can do that very quickly. And we can train the machine for new concepts, new relations within a couple of weeks. But the machine is sort of intuitive enough for someone who is, again, like me, not an IT person, to train this machine very quickly to performance levels of human precision. And that's, I think, another sort of really important factor compared also to our competitors. We're doing these projects, in this case, the imaging project, obviously also with partners. We're currently in talks with one of the very biggest teleradiology clinics in Europe, where you can imagine that imaging plays a big role in terms of increasing productivity. And there you need a tool that also can sort of basically be put between the image and the image reader and learn from how a human is actually reading, for example, chest x-rays. And what a feature that our technology has is what we call unsupervised learning. So you don't really have to train the machine at all. The machine is learning from human examples. So in terms of annotated, curated text the machine needs to learn new concepts, we're talking about hundreds and not thousands or 10,000 examples. We're talking about very small numbers of annotated text or images for the machine to pick up new technologies.
A few years.
We're already getting to the end. So what I'm actually trying to do is, because I mentioned all of these points already, maybe I can use the rest of the time to show you very quickly how the machine looks like, and bear with me. I will try to do this now because, again, due to the old world problems we had before, my own computer didn't work. So I'm trying
social media
this one here.
Because they're like, no, you can do that. Do this, and people are like, what are you talking about?
Possible.
They're sharing content.
There we go. I'm not sure if we can see already the screen. No, not yet.
Yeah, I think we'll see here.
Mouse is kind of helpful. There we go. So, oh yeah, there we go. Okay, so here you see already how the workbench looks like. And let me just go back one step. So again, now we're live. You see that I'm logged in with my name. And the way it works, really, it's a modular system, and you see each of these tiles represents one analysis. And you can go through all different analyses. For the interest of time, I'll show you just one of them here, or maybe two, depending on how much time we have.
That's weird.
But here again, you see the structure that I showed to you already. So you see again on the left-hand side, you would define what kind of sources you would be mining data in, and I'll just show you how that looks like. If you wanted to add a new source and you would use another importer, I'll show you what kind of imports are already available right now. So you see here that I mentioned there's PubMed in here, clinicaltrial.gov, but you could also go to non-medical things like LinkedIn, to Twitter, to Wikipedia, whatever you want to mine in, you can sort of select the type of data you want to do, and if you wanted to go into PubMed, for example, you can do that.
Basically, all the press we got was from me and not them. I'm like, screw you guys. I'm like,
so it's a very sort of. Usually, the customers require, if you were wondering, sort of a day of a sort of intense workshop, and then they can run this machine by themselves. So it's really intuitive. And here you see the search interface for PubMed. It looks like the website itself, so you can search for full text, for titles. You can decide whether you want to look only at abstracts or whether you want to look at the full text. So it's all pretty much intuitive also for people who are not used to sort of write their own code, which obviously you don't want the people to do. And once you have decided what kind of data you want to use, actually let me close this again here, because we don't want to confuse anything. You would then define what kind of analysis you want to do. This is the thinker phase, and I'm just doing a sample here, so you see how that looks like. Secondary thinker here. I would configure that, and then what you could see, I can do this here. Oh, there it comes up. Okay, so you have a set of entities and relations that you can pick from, and in the interest of time, I'm not going through that, but this is the way you would do this. And if I close this thing again, I know people are already waiting. Maybe if I can show one last thing. In the visualization space, you have a way of sort of showing what you're looking for. And I'm showing here an example from the imaging learning space. So I'm having a histology slide here, and I'm showing you just a demo of how we would train the machine to learn new features in histology. So I'm doing it very simple now, like with a child's pen, marking this glandular cell here, and just giving the machine just one little sort of hint of what it's supposed to look for. And now I'm telling the machine to actually learn from this example. And this is all live now, so it's coming up with a first way of doing it. So you see, it's already starting to learn from it in an iterative way. You would continue doing that. So you could then sort of form the next one, and go from there, and then have it iteratively learn from this. And I think this gives you sort of good understanding of what the state of the art is in terms of machine learning right now, how quickly machines can actually learn from examples, and how quickly you can get them better. And this is true for both text and images. And with that, I think I have to stop. Thanks so much. Thanks for bearing with me. And thank you. Thanks.